All right, howdy. So we're back, and now we're going to talk a little bit about what kinds of molecules we can see when we make these covalent molecules. So H2 is hydrogen gas. Hydrogen gas is a diatomic molecule, and that means it contains two atoms. Diatomic. The di is our prefix for two. Nitrogen gas is N2, oxygen gas is O2, and the halogens, fluorine gas, chlorine gas, bromine is actually a liquid, and iodine is actually a solid. These are all naturally diatomic. So if you find these elements in nature, you will find them as diatomic molecules. You won't find H floating around by itself. Hydrogen gas is H2. You won't find nitrogen floating around by itself. It's N2, nitrogen gas. So these are all diatomic molecules. And we can also call them homonuclear diatomic molecules because both atoms are the same element. H2, N2, O2, they're all the same element. They're homonuclear, meaning the same. Heteronuclear diatomic molecules include hydrogen chloride or carbon monoxide. So these are diatomic molecules that have two different elements making up the different atoms. So this is a little picture of, so I just realized that I'm not in full screen. Hold on. Sorry about that. For this slide, it didn't make too big of a difference. There's nothing too small on here, but anyway, heteronuclear diatomic molecules. This is a example. This is carbon monoxide. I will explain the coloring of the different balls in the model in a couple slides. But heteronuclear means there's two different atoms in the diatomic molecule. And then molecules which have more than two atoms are called polyatomic molecules. O3, which is ozone, and white phosphorus are elemental versions of polyatomic molecules. So O3 is an element. Ozone, you find that it's just oxygen atoms bound together, three of them. White phosphorus is also considered an element, and it is 4 phosphorus atoms put together to form a polyatomic molecule. But we can also have polyatomic molecules with different atoms. They don't have to all be the same. So water is an example of a polyatomic molecule. It's got 2 hydrogen atoms and an oxygen atom. That's what our subscripts tell us for water, H2O. We got 2 hydrogens and 1 oxygen. And methane is another example, a simple example of a polyatomic molecule. That's 4 hydrogen atoms and a carbon atom makes methane gas. And here's a little picture of a space-filling model. I'll explain that in a couple slides of a polyatomic molecule. All right, I guess not a couple slides, just one slide. Molecular models are used to examine the 3D structure of compounds and how they interact. So we draw these models because obviously atoms are really, really small. We can't see them, but we do like to visualize the 3D structure of the molecules. We'll go into that a lot more in chapter 6 and 7. But basically, we use these models to simulate the structure of the compounds and also to sometimes look at how they interact with each other. So there's a few different versions of these molecular models. There's the wedge and dash version. So the wedges, like this one here, those are simulating that the hydrogen atom is coming out towards you, whereas the dash on the other side, that other hydrogen, is going away from you. So that is to simulate the 3D structure on a 2D piece of paper. ball and stick models are a little more elaborate. In this case, we have different balls representing the different atoms. So over here we have some color options for our different atoms. These are very commonly used colors in molecular modeling. Carbon is usually black or gray. Here it's kind of a grayish in my picture, but it's usually black or gray. Hydrogen is almost always white. I've never really seen a molecular model where hydrogen's not white. And oxygen is usually always red. So we've got some oxygens, carbons, and hydrogens in this ball and stick model. And the sticks represent the bonds between the atoms. So this is a compound, molecular compound that has many different bonds between carbon atoms, carbon and hydrogen atoms, and carbon and oxygen atoms. And then one little bond between an oxygen and a hydrogen on the end here. And that's the ball and stick model. And then we also have something called the space filling model. This is the same molecule for all three representations, actually. So the top is the wedge and dash structure or model. The middle is ball and stick, and then the bottom one here is the space filling model, and they're all for the same molecule, but the reason that we would maybe want to use the space filling model is if we want to look at the volume taken up by these atoms. So the ball and stick version is not very accurate, and the wedge and dash version is not very accurate based on the sizes of the atoms compared to the length of the bonds. It's not very drawn to scale. But the space filling model is a little bit better. You can't really see the bonds anymore, but they are inside of the space filling model, and that's more representative of what the molecule will actually look like. So it depends on what you want to look at, what kind of model you would want to use. So if you want a realistic version of the volume of the molecule, then I'd use the space filling. If you want to look at different bond angles and bond lengths, then I would look at the ball and stick model. And if you just want to know what the structure is, I would probably use the wedge and dash version, because then you can see all of your atoms and you don't have to remember different colors or anything. They're just labeled right there for you. All right, so I mentioned before that we have different kinds of elements. So the diatomic gases, or the diatomic molecules, those are often atoms, or sorry, not atoms. Those are often elements like O2, H2, N2, F2. These are all diatomic elements. Some elements do come as single atoms, and those would be the noble gases like helium, neon, argon, etc. They come as single atoms. Sometimes we have these 3D metallic lattice structures like we saw way back in chapter 1. We have these metallic solids that often come for like sodium or magnesium, those kinds of elements. And then sometimes we actually have these weird complex 3D networks too. And we see those with things like sulfur, phosphorus, carbon even can make these weird structures. So elements can come in lots of different forms. Sometimes the same element can even be found in several different forms. So sometimes we can find carbon in different forms, not all the same, not all like this or all like this, but some of each. And these are called allotropes. And here are some different allotropes. Sorry, it's a little grainy, but diamond is made out of carbon atoms, and it has a very ordered structure. Graphite is made out of carbon atoms, all carbon, only carbon. These are all elemental forms of carbon. Graphite is what you find in like the lead of your pencil. So graphite has these layers of structure. So they're flat layers. And then you can even find carbon in the form of a buckyball. Buckyballs are super cool. It is 60 carbon atoms, all sort of bonded together. They're not really bonded, but these carbon atoms form this really cool network that looks kind of like a soccer ball, and we call that a buckyball. It was named after the guy who found it, his name was like Buckminster or something. So it's called a buckyball now. So these are all allotropes of carbon. Oxygen gas and ozone are two allotropes of oxygen. White phosphorus, we talked about a little bit, was phosphorus 4, so P4, but there's also red phosphorus, and red phosphorus is found in this really weird chain structure. So those are two allotropes of phosphorus. And sulfur can also be found as this 8-membered ring, so S8, or we can find really long chains of sulfur as well, and those are different allotropes of sulfur. Okay, so allotropes are pretty interesting. It just depends on where you find them in nature. Like if you have graphite and you put a whole lot of pressure on it for a really long time, you'll end up with diamond eventually. So you can go from one allotrope to another. And that's kind of what happens in the atmosphere with ozone as well. So allotropes, good thing to keep in mind. Elements come in lots of different forms. Sometimes the same element comes in lots of different forms. Anywho, let's talk about molecular formulas. So we discussed the chemical formula for ionic compounds. Now we're going to talk about molecular formulas, and these are specifically for covalent compounds. So molecular formulas include the element symbols and subscripts to show you how many of each atom are in the molecule. For example, glucose, which is a type of sugar, that has 6 carbon atoms, so it's C6, H12, so 12 hydrogen atoms, and 6 oxygen atoms, O6. So C6H12 O6 is the molecular formula for glucose. And it has those ratios of carbon, hydrogen, and oxygen every time for every molecule of glucose. It's always the same. Empirical formulas, on the other hand, reduce these formulas to the simplest whole number ratio of the elements. So empirical formulas, the empirical formula for glucose would instead be just 1 carbon atom, 2 hydrogen atoms, and 1 oxygen atom. So we took all of these and found the common denominator. So we divided by 6 and ended up with 1 carbon, 2 hydrogens, and 1 oxygen. That is the simplest whole number ratio of the elements. So that is the empirical formula. So in a couple sections later in chapter 5, we're going to be talking a lot about molecular formulas and empirical formulas and how you can find those, how you can actually calculate those from different experimental data. So specifically like combustion data. So we can burn a sample and get the products of that reaction and we can then tell based on the analysis of that what the empirical formula was of the thing that we started with. And once we have the empirical formula, if we know the molar mass, so this is molar mass of the molecule. We learned about molar masses of elements, but when we have the molar mass of the molecule, we can get the empirical formula back to the molecular formula. So the empirical formula is something that we can find experimentally, but the molecular formula is the one that tells us a little bit more about the compound and how it reacts and things like that. So the molecular formula is more like the true formula for the molecule. And then on the right here, I just have a graphic from your textbook that shows a few different compounds and their molecular and empirical formulas. So water is H2O2, or sorry, I'm sorry, water is H2O, as you surely know already. And this is what a model of H2O looks like. The one oxygen atom is the red ball, and the two hydrogens are off the side of the oxygen. And the empirical formula is the same as the molecular formula. So sometimes that happens where H2O is the simplest whole number ratio of the elements, so it's the same. And we will be learning about why the water structure looks like that and not like a straight line. We'll be learning about that in Chapter 6 and Chapter 7 as well. Anyway, hydrogen peroxide, the one that I actually mentioned ahead of schedule, was hydrogen peroxide is H2O2. There's a little joke that you might have heard before where someone goes into a bar and asks for H2O, and then somebody else goes into the bar and asks for H2O2, and then they die because H2O2 is hydrogen peroxide. Instead of saying, I want H2O also, he said, I want H2O2, which is poisonous, and he died. Anywho, just a joke you might have heard before. If not, feel free to spread it around. It's not that funny, but chemistry jokes are not always that funny, but we try. So H2O2, hydrogen peroxide, looks like this in its molecular model. In the empirical formula, there's two hydrogens, two oxygens, so the simplest whole number ratio is just HO. So it has a different molecular model and empirical formula than water. And then we have ethane, which is 2 carbon atoms and 6 hydrogen atoms. Propane, which is 3 carbon atoms and 8 hydrogen atoms. We will talk a little bit more about those in a couple slides. Those are called organic molecules. They're specifically hydrocarbons because they're just made out of hydrogen and carbon. But both of those, so ethane can be reduced. So C2H6, we can divide by 2 and end up with C1, so CH3. And so that's the empirical formula for ethane. Propane actually ends up with the same empirical formula as it started with because 3 and 8 don't have any common denominators, so there's no simpler whole number ratio of those two. Acetylene is another type of hydrocarbon. So acetylene is C2H2. So we got 2 carbon atoms and a hydrogen atom. And those 2 carbon atoms in the middle are triple bonded. We'll be talking more about the different kinds of bonds you can make in Chapter 6. But since there's C2H2, we can divide by 2, and our empirical formula is just CH. And then finally, benzene. Benzene is a fun molecule because it's this cool little ring. It's a hexagon, but we call it a ring in chemistry. And that's C6H6. We've got double bonds between some of the carbons, but not all of them. So we've got some hydrogens on there as well. So C6H6, we divide by 6 and get our whole number ratio of CH. So if you look, that's actually the same whole number ratio that we had for acetylene. So these two very different molecules have the same empirical formula. So you can see that there's a little bit of a problem here when we are determining empirical formulas experimentally from our combustion data, that we could be looking at either benzene or acetylene, but these are two very different molecules based on their molecular formula and their structure. So we would need more information to be able to tell which one it is that we were analyzing. So there's a good example of the difference between molecular formulas and empirical formulas. And we'll talk more about that later in Chapter 5. There's also something called a structural formula. So this we won't get to too much right now. This comes in really handy with organic chemistry. And we will see it a little bit more when we learn about Lewis structures in chapter 6. But for now, a structural formula shows you how the atoms are connected in the molecule. So we've got these lines connecting the different atoms representing our bonds, and structural formulas can actually tell us about which atoms are bonded to which. Whereas if we had C2H4O2, there's 1 carbon, 2 carbons, then 4 hydrogens, and 2 oxygens. So if we just wrote it out like this with our molecular formula, you wouldn't really have any idea which atoms are bonded to which. So a structural formula looks like this, but the more common way that you'll see a structural formula is in a condensed structural formula, which is still kind of written like a molecular formula, but it lists the elements in different groups to show the connectivity. So we write CH3 together to represent this part of the molecule, this carbon bonded to 3 hydrogens. And then we have COOH as the other group in our condensed structural formula to show that we've got a carbon bonded to 2 oxygens, and then our oxygen is bonded to a hydrogen at the end. So these condensed structural formulas are really helpful for organic molecules in particular, as we'll see when we move on a little bit here. All right, so we talked about binary ionic compounds. There's also binary nonmetals, and the naming is a little bit different for these binary nonmetals. So these covalent compounds, the naming works a little bit different. The first part is the same, so the first word in the compound name is the first element in the compound formula. The second word in the compound name is pretty similar, so the second word in the compound name is the name of the second element where we change the ending to "ide." So far it looks pretty similar to ionic compounds, except that we have 2 nonmetals. So we have the first nonmetal written out completely, and then the second nonmetal we have with the "ide" ending, just like we did before. But the difference with covalent compounds compared to ionic compounds is that we use these prefixes to indicate the number of atoms in the formula. So carbon monoxide has a carbon with 1 oxygen. So the mono prefix tells us there's 1 oxygen. Carbon dioxide, if we were talking about ionic compounds, carbon oxide could correspond to either one of these. So when we talk about the covalent compounds, we specify using these prefixes. So carbon monoxide is different than carbon dioxide. So carbon monoxide, we had 1 oxygen. Carbon dioxide, we have 2 oxygens. We can go further. There's also carbon tetrachloride. So I can actually show you which ones are which here. So this is 1 carbon, 1 oxygen. This is 1 carbon, 2 oxygens. So now our carbon tetrachloride is this one down here. We've got carbon and 4 chlorine atoms. So the tetra tells us that there's 4. So tetra is our prefix for 4. And then we have dihydrogen monoxide. We don't always put the prefix in the beginning with the first element, but hydrogen ones are a little bit weird, as it says in your textbook. So sometimes we call water dihydrogen monoxide. Usually we just call it water, but there's 1 oxygen and 2 hydrogens. So we still have the monoxide part for the 1 oxygen, which is the second element in our formula. So these prefixes are used for naming these binary nonmetals or these binary covalent compounds in the IUPAC system. Here it is. I said IUPAC before, but here's what it stands for: the International Union of Pure and Applied Chemistry. So this is that nomenclature thing that I told you about before, where chemists are very particular about what we call things. And these are all the prefixes. They're different than the metric prefixes, unfortunately, and that can't help you remember these, but they're pretty commonplace things, I would say, that we tend to use in, you know, common culture. Like a tricycle has 3 wheels, so tri. Or let's see, we have a pentagon with 5 sides, a hexagon with 6 sides, a heptagon with 7 sides. So when we're talking about geometric shapes, these all come from those prefixes. Tetra is one that's a little weird. That comes from a tetrahedron, which is another geometric shape, 3D geometric shape actually. But these prefixes, you should try and remember some of these at least. Mono, di, tri, tetra, those are all pretty important to remember. Those will come up a lot when we're naming different compounds. When we start to go bigger, we don't use those as often. And then some compounds have common names that are used more often because of historical usage, particularly water, hydrogen peroxide. These things, when we call them water or hydrogen peroxide, they really have literally nothing to do with the nomenclature of typical binary nonmetals or covalent compounds. You wouldn't know where they got the peroxide or where they got water at all from this naming system, but we use these because they're very commonly used compounds. So people use them all over. And since we've been using them for so many years and in so many places and in so many applications, the new naming system never really caught on for these. So water, hydrogen peroxide, ammonia, these are 3 of the more common ones. And then hydrazine and nitric oxide, not as common, but these, yeah, the new naming system never caught on for these compounds and some other hydrogen compounds that are written in your textbook. So one other distinction that your textbook makes with hydrogen-based molecules is inorganic acids. So an acid, the definition of an acid, there's a few different definitions, but one of the most common definitions is that an acid produces the hydrogen ion when it's dissolved in water. So you dissolve the acid in water and you get an ionizable hydrogen. So the hydrogen ion is one of the products when you dissolve in water. So these inorganic acids contain hydrogen and 1 or more other nonmetals. So their chemical formulas always start with hydrogen so that you can see that that hydrogen is going to come off. So here's some of those inorganic acids. So HF, HCl, HBr, HI, these are all inorganic acids. They start with H, and the binary compound name, the IUPAC name that we would call them, this is what we would call the gas form of these molecules. And that is just hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, just like we learned the nomenclature a couple slides ago. But the inorganic acid always has this other name: hydrofluoric acid, hydrochloric acid, which I'm sure you've heard of, hydrobromic acid, hydroiodic acid. So hydrofluoric and hydrochloric are the 2 most commonly known ones that you might have heard of before. Hydrofluoric is a particularly bad one. I mean, all acids can be really bad depending on their concentration. But hydrofluoric acid is a particularly bad one, and we'll talk about that uh, quite a bit later in the semester. All right, so I mentioned hydrocarbons before, so I'm just going to go over them again. So in more detail, a class of covalent compounds made up of only carbon and hydrogen are called hydrocarbons. Makes sense, right? These are organic compounds. Um, there are other types of organic compounds. The main definition of an organic compound is that it contains carbon. Carbon is very essential to organic matter and organic life forms. So everything, every living thing has carbon in it. So organic compounds, they usually contain carbon and hydrogen, but they can also contain oxygen and nitrogen in addition to carbon and hydrogen. So glucose, for example, the one we saw before, was C6H12O6, so it had oxygen as well as carbon and hydrogen. And hydrocarbons often have special names that don't follow those IUPAC rules that we learned before. Well, I'll actually correct that. They do follow the IUPAC rules, as you'll learn if you continue on to organic chemistry, but they don't follow the simple nomenclature of ionic or covalent compounds. They have special names, but those are very well distinguished, and those are commonly accepted by the IUPAC system as well, but they're different. They're different than what we would expect. So hydrocarbons, one of the special categories of hydrocarbons are alkanes. Alkanes mean that we just have single bonded carbons and hydrogens. And those alkanes always have the formula of CnH2n plus 2. So we've got, if we have methane, for example, all of our alkanes end in ane, so they're easy to remember. We've got 10 of them here, for example. So methane has one carbon, so that'd be C1. So our H is 2 plus 2. So 2 times 1 is 2 plus 2. So we got CH4. Ethane is C2H4 plus 2, because we got 2 times 2 now, so 4 plus 2. So ethane is C2H6, and that is the formula that works for all alkanes. I won't do the rest of them, but it works for all of them, I promise. And these are the structures over here to show you in model form. It's a little hard to see. You can see it better in your textbook where they're bigger, but I wanted to show you them here too. So these are all single bonded carbon and hydrogen molecules. So the carbons are all, they have single bonds between each carbon and single bonds to all of the attached hydrogens. So other hydrocarbons have different special names. So if there are double bonds involved, we call them alkenes. If there are triple bonds, we call them alkynes. So those you don't need to know about, but that's how this naming system works. So we've got methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane here. And these prefixes, not the same prefixes as the other slide, unfortunately, but you don't need to memorize these. These, just for your knowledge, some of them are the same. Hex and hept, oct, non, dec, those are the same. So the first four are not. So methane means there's one carbon, ethane is 2 carbons, propane is 3, butane is 4, and then the rest makes sense. Pentane 5, hexane 6. So those first 4 are just the common names that have been stuck with those compounds for many years. So what else can we talk about with organic molecules? So you guys will hear so much more about this if you continue on to organic. You will be experts at identifying functional groups, I promise. But organic molecules are made up of different functional groups. These functional groups determine the reactions that the molecules undergo. So if you went on to organic chemistry, you'd learn about how different functional groups are involved in different mechanisms, reaction mechanisms, so where we can plot, we can basically track all of the different steps of a reaction, you know, atom to atom, electron to electron detail. You don't need to know that in general chemistry, but we can do that. You will learn how to do that if you go on to organic chemistry. And those reaction mechanisms are all based on functional groups. Anywho, there's 4 different functional groups that your textbook decided to tell you about, and those are alcohol, aldehyde, carboxylic acid, and amine. There are more functional groups, but you don't need to know those. So an alcohol is an OH bond at the end of the molecule. So our oxygen is the red atom here, and hydrogen is the white atom or the white ball in our model. An aldehyde, on the other hand, is a CHO functional group. So that means there's a carbon double bonded to an oxygen. So carbon is our black or gray ball here, and oxygen is our red, and hydrogen's over here. So we have a carbon that is double bonded to an oxygen and single bonded to a hydrogen at the end of the molecule. So there could be like a bunch of other stuff over here. But at the end of the molecule, we have this carbon double bonded to an oxygen, single bonded to a hydrogen. That makes it an aldehyde. Carboxylic acid is kind of similar to an aldehyde. We've got double bonded carbon to an oxygen, but then instead of just a hydrogen on the end, we've got a oxygen with a hydrogen attached to it. So that's why we call it COOH. So there's basically one of the O's here, one of the O's there, and then the H tags on to the end oxygen. So this is called a carboxylic acid functional group, and there's a bunch of other stuff over here, but at the end of our molecule, we have this carbon with 2 oxygens and a hydrogen on the end. And finally, the other one that they wanted to tell you about is the amine functional group. An amine is basically anywhere in the molecule where you have a nitrogen attached to hydrogens. So there could be other stuff on either side. Then the amine could be on the end of the molecule, but it doesn't have to be. But basically, it's just a nitrogen atom with hydrogens off of it, 1 or 2 or 3 hydrogens coming off of that nitrogen atom. And that's what makes it, and that nitrogen makes it an amine. So for example, here is a molecule that you might know about without knowing that you know about it, and that is ethanol. So ethanol is found in alcohol, and I don't mean the functional group alcohol, I mean like the drink. Ethanol is what makes it alcoholic, and ethanol is an organic molecule, and the "-ol ending tells you that it has an alcohol functional group. Maybe that's where we came up with the term alcohol for stuff that you will drink someday when you're old enough. But ethanol, the ending comes from the fact that it's got an alcohol functional group, and the ethane part is telling you that it's got these 2 carbons, and it's kind of like a hydrocarbon with an alcohol group on the end. So we put together ethane and alcohol to get ethanol. Pretty cool, right? So organic chemistry, that's as far as we're going to get with organic chemistry pretty much. But that's your teaser for future semesters if you keep going with chemistry, which I suggest because chemistry is cool, super cool. And then this is just a review slide for you to tell the difference between covalent compounds and ionic compounds. Covalent compounds contain only nonmetals, and they're named using these prefixes. Ionic compounds, the ones we learned about first, those could be monoatomic ions or polyatomic ions, which we will learn more about later. We didn't get into polyatomic ions yet, but you'll hear about them soon. And ionic compounds usually contain metals and nonmetals. So like a metal bonded with a nonmetal, that's a binary ionic compounds, but you could have multiples. You don't need one of each. I don't know why that slash is there. They aren't named using the prefixes. We had like iron chloride. So iron 2 chloride, for example. We didn't use a prefix for that. It's not iron dichloride, it's just iron chloride, or iron 2 chloride to specify the charge on iron. Whereas carbon monoxide has that prefix of mono at the beginning to tell you that it is one oxygen and not two oxygens like in carbon dioxide. And then, oh, I got ahead of myself here, Roman numerals in parentheses for those transition metals to tell you what the charge is on that cation. Okay, cool. That's it. Sorry this was a little long and super late, but I'll see you tomorrow, or probably today, depending on when you watch this. See ya.